Hello friends, once again I Professor Bharat Kangude welcome you all for the discussion on multiple choice questions of chapter number 3 from atomic and molecular physics. In earlier two videos we have discussed few important conceptual multiple choice questions on chapter 1 and chapter 2. Chapter 1 was related to this hydrogen atom model. Basically we have seen Bohr atom model and hydrogen spectrum, whereas in chapter 1 we have seen alkali spectrum. The electrons in the outermost orbit is unpaired single electron, so such type of systems are called as alkali spectrum, and the sodium spectrum as an example of that we have discussed there. In the chapter 3 we are now having two valence electron system, and this time there are all alkaline earth elements. So this is two valence electron system, and its spectrum is a bit different than the spectrum what we observed in case of chapter 1, that is hydrogen spectrum, and chapter 2 where it is an alkali spectrum, or an example we have taken this to be a sodium spectrum. Now what are the differences, how to go for application of this LF's coupling schemes there, how to go for calculations of the term values, etc. And there are certain rules over which all these MCQ or multiple choice questions are dependent. So let's try to solve some of the important questions one by one. Now this is a chapter 3 two valence electron system. Question 1: following is not an example of two valence electron system element. So we have to identify out of the given four options which element does not fall in the category of alkaline earth element or the two valence electron system. So here option A is beryllium, option B is magnesium, option C is calcium, and option D is potassium. So out of this, from our knowledge in chapter 1, sodium, potassium, cesium, etc., these are the elements which are called as alkali elements, and these are having one valence electron, or this is what one electron system, atom system. So therefore in this group, beryllium, magnesium and calcium, all these are the alkaline earth elements which are having two valence electrons, and therefore in this particular group of these elements the potassium doesn't fit. So here it is not an example of two valence electron spectrum elements, and therefore correct option of this is this D. So all other elements are these alkaline earth elements. So in periodic table you might have seen location of all these elements, and these elements have a specificity that in its outermost orbit there are two unpaired electrons, and this is called as a two valence electron system. So potassium is not part of this. Now again a very simple and common example: alkaline earth element contains valence electrons in the outside closed shell. As we have seen, when it is 1, it is one valence electron system, when it is 2, it is two valence electron system. 3 and 4, these options are not at all applicable, and therefore correct option of this question number 2 is 2. So alkaline earth element contains two valence electrons in the outside closed shell. For example, another example here, one can go for this helium 2. Helium has its electronic configuration as 1s2. Likewise there are beryllium, there is calcium and other elements which are having also in their outermost orbit two unbalanced electrons or unpaired electrons, and that is why these are called as two valence electron system. Then there are, now we have to apply this LS coupling scheme according to question number 3. According to LS coupling scheme, quantum mechanical angular momentum L1 star and L2 star are quantized with respect to each other in such a way that they form the resultant L star is equal to vector addition of L1 star plus L2 star. So in earlier chapter we have seen this L1 star is given by quantum mechanical angular momentum is given by L1 into L1 plus 1 into h upon twice pi, where L1 is nothing but the orbital angular quantum number of electron 1. Similarly, L2 in this case, it is also given by root of L2 into L2 plus 1 into h upon tau square. Now, according to this coupling schemes, the angular momentum L1 star and L2 star are quantized with respect to each other in such a way that they form the resultant. So L bar star, this is actually L star bar is equal to L1 star bar plus L2 star bar. So this is actually a vector addition, and therefore in the vector addition, when we go for both of these vectors, addition of these vectors, this addition of vector gives you sometimes minimum addition when this L1 and L2, okay, L1 minus L2, L1 star and L2 star is equal to 0, or that is minimum. So when these two vectors are completely anti-parallel to each other, and maximum we get when this L1 star plus L2 star is added, and we get this quantity is to be maximum. So naturally 0 to L1 plus L2, that is not valid. 0 to L1 minus L2, this is again not according to this quantum mechanical principle or quantization principle. And what is true in this case is this. So value of L, capital L bar varies from L1 star minus L2 star, this is minimum, to L1 star plus L2 star, that is the maximum. So in energy diagram, if have this is L1 star and this is L2 star, okay, suppose this L1 and L2 are having same magnitudes, then addition of this gives me this vector. So this is the addition of this vector L1 and L2 when they are in the parallel direction. This is the maximum addition. And when this L1 star and L2 star are anti-parallel, in this case I'll get 0 vector here. If magnitude and direction of these two vectors are same and directions are exactly opposite, we will get this to be a minimum. So that is how, according to this LS coupling scheme, quantum mechanically these two vectors L1 star and L2 star, they add in such a manner at one position, at one addition we will get minimum component resultant, and at another it is possible to have this maximum addition, and in between values are also possible if this quantization principle is valid there. So this is what LS coupling scheme in case of the two valence electron system we have to apply. In the next of the few example, we are going to see lot many such examples where we have to calculate, or we have to add this L1 star, L2 star, sometimes S1 star, S2 star, and we have to get J1 star, J2 star, or we can get L1 star, L2 star, etc. So this type L star and capital S star too. So which scheme we use, either LS coupling scheme or JJ coupling scheme, based upon that we have to go for numerical examples as follows. So let's come to this question number 4. According to LS coupling schemes, now these are actually values given. L1 is equal to 1 and L2 is equal to 2. Then the resultant. So according to this theory, this resultant is given by modulus of L1 minus L2 up to modulus of L1 plus L2. And here we have to use this quantization principle. That means the L bar should take quantized values in such a manner. So adding this 1 and 2, I'll get it's the difference between L2 and L1, modulus of this. So L1 minus L2 is minus 1, but modulus of that is plus 1. And when we go for addition of this L1 plus L2, that is maximum, this is going to be 3. And 1 and 3, they are separated by 2. So in between, two values possible. So difference here is 1, difference here is 1. And therefore, these are the three possible values of capital L bar when this L1 and L2 added together vectorially. So vector addition of L1 and L2 gives you three possible values, that is shown by this particular diagram. In vector atom diagram, we draw this. This is L2 is equal to 2, and if suppose I take this L1, now this is in L1. So or you can take any direction of this L1. L1 is equal to 1, half of this vector. Now when we add these two vectors, this addition can be shown of this way. So this is what value of this is a vector L2 is equal to 2, and this vector L1, now this L1 vector is equal to 1. it takes different directions as shown and the resultant is different. Now in some case when we add this L2 plus L1, we get this to be vector 3. In other case it is possible, this orientation is possible of L1, then I'll get this addition will be equal to 2, and sometimes this orientation of L1 is also possible here. So this is going to be resultant is capital L is equal to 1, this is L equal to 2, and this is L equal to 3. So that is how capital L equal to 1, L equal to 2, L equal to 3, this type of vector additions gives you. So orientation of L1 with respect to L2 is such that the resultant is obtained to be either 1 or 2 or 3 as shown by this diagram. So this is what a speciality of this LS coupling scheme. These vectors L1 and L2 add in such a manner the resultant can take values like 1, 2, 3. So therefore option A, B and C are not correct. These are individual additions. So total addition will be either 1 or 2 or 3 depending upon the direction of L1 bar and L2 bar. So this orientation plays a important role, and accordingly the resultant may get different values. So possible addition values of this L1 and L2 in this case are shown to be 1, 2, 3 as shown in this particular example. Now question number 5. According to LS coupling schemes, we have S1 is equal to 1/2 and S2 is also equal to 1/2. Then the resultant. So here also we have to go for this principle. Capital S is going to be modulus of S1 minus S2 as well as up to modulus of S1 plus S2. Since in both the cases S1 and S2 are 1/2 and 1/2, so I'll get a resultant, minimum resultant will be simply equal to 0, and when I add 1/2 plus 1/2 I get a maximum value is equal to 1. So in between fractional value is not allowed. So fractional value for capital S is not allowed. Okay, this is what a quantum mechanics tells you. This S bar takes only quantized value 1 into H cross, 0 into H cross, 2 into H cross and 3 into H cross, like that. So 0.5 into H cross etc. is not possible, and therefore accordingly we have only two values for capital S according to this vector addition, and therefore it is 0 and 1. So this last option D is the correct option for this question number 5. When we draw this diagram, now I have this is S1 is equal to half. Similarly, I have this S2 is equal to also half. So there is a possibility these two are added together, and that will give me S1 plus S2 is equal to capital S is equal to 1 as shown by this diagram. Sometimes when they are anti-parallel, when I go for this anti-parallel case, this is S1 is equal to 1/2, S2 is equal to 1/2, they will added in such a manner that capital S is equal to simply 0. So that is how vector addition of S1 and S2 also follows all the rules of vector additions and quantization principle of quantum mechanics, and that's why it gives the resultant S bar is equal to simply 0 and 1. So we have taken these two examples just to understand how LS coupling scheme is applied for a two valence electron system. In two valence electron system we take several examples like PD configuration, we take SP configuration, we take DD type of configuration, or like that. So one electron is in the P configuration, another electron is in D, here one is in S and another is in P, like that. Based upon that, value of L1, S1, L2, S2 go on changing, and accordingly this capital L as well as capital S or capital J take different values. That is what we call as a term value. So that is what we are going to do in further example. Question number 6, very simple question here. According to LS coupling schemes, if we have L is equal to 1 and S is equal to 1, so total orbital angular momentum of the system, capital L is equal to 1 and capital S is equal to also 1, then the resultant spectral terms are, so these are called as either term values or spectral terms. So since L is equal to 1, this must be a P state. Since S is equal to 1, we have multiplicity M is equal to twice S plus 1. Making this simple calculation, that gives me 2 into 1 plus 2. That means all these things, 2 plus 1 is going to be 3. That means all these terms values obtained here will be of the triplet. So these are going to be triplets. So this is triplet, this is P state, so I'll get here triplet, and then this is P state, or that is the P state because L is equal to 1, and we have to go for a calculation of J. J is given to be addition of L bar plus S bar. This is a vector addition. Here also this addition is given to be maximum to minimum. So it is L bar minus S bar up to L bar plus S bar, vector addition. So addition of 1 and 1 is maximum 2, and L minus S, subtraction of 1 and 1 is similarly 0, and in between value possible is 1. So 0, 1 and 2, these are the three different values possible for J, and therefore in this term values we are writing triplet P, and this is 0, 1 and 2. So this is what the term values we are obtained. Actually we will having triplet P0, then we will have triplet P1, and then finally we will have triplet P2. These are the three possible term values in a case when this capital L and capital S is equal to 1. The resultant term values are shown like this. So out of these examples, option A is triplet 0, 1, 2. That means these are the three terms. Option B is triplet 1, 2, 3. This is not possible according to this theory what we have seen here. So this is not correct option. There cannot be a question of D or state, as well as there is not a F state at all, because in here this L is equal to 1, therefore it is a P state, and therefore correct option of this question number 6 is A. It is triplet P0, 1 and 2. So that is how we have calculated term values of two valence electron system in using this LS coupling scheme as shown here. Now let's go for this is a PD configuration. So as I said, one electron is in the P state and second is in the D state. So naturally I will get L1 is equal to 1 and S1 is equal to 1/2. Similarly for the second electron here, L2 is equal to, since it is P state, D state, so it is L2 is equal to 2 and S2 is equal to 1/2. So when I use this LS coupling scheme, I have to go for addition of capital L is given by L1 bar plus L2 bar. So this addition is a vector addition, and that gives you maximum value of L1 plus SL2 to minimum value L1 minus L2. According to we have to calculate this L. Similar is to be done for S. S bar is also given by S1 plus S2 up to S1 minus S2. So that way also we are going to calculate L and S, and when we go for addition of this L and S, capital S, we get capital J values. Here we actually, when we go for in this entire calculation of L1 bar plus L2 bar plus S1 bar plus S2 bar, then addition of this L1 this capital L and capital S, we get in all actual term 12 J values or 12 term values are possible. So 12 term values, or actually this J is supposed to get 12 values. Out of that, some terms for which this we can go for this entire calculation in the theory as well, and that shows three singlets are there. There are three singlets. We can get actually all the singlets if we have a time, and we'll get 9 triplets, and in all total 12 singlets and triplets will be possible. So that is how we will get 12 total terms. So in PD configuration of two electrons in LS coupling gives in all, these are total 12 terms. We can calculate this using this LS coupling scheme. Out of these are 3 triplets and remaining are 3 singlets and 9 triplet. So correct answer here is A, that is 12 terms. Out of these 3 are singlets and 9 are triplet. Just to confuse you, I have given 12, 12, 12 everywhere. That means we are supposed to get 12 terms in any of the combination here, and 9, 3, 8, 4, 4, 8, etc. These combinations are not allowed at all. So this vector addition tells you of these vectors or different quantum angular momentum vectors of this P electron and D electron. That gives you total quantum terms or spectral terms is equal to, or term value is equal to 12. Out of that 3 are singlets and 9 are triplet. So that can be understood from a simple example. Now for D electron, following are the quantum values. Now D electron, so it is a D electron means the electron is in the state where its value of L2 or L1, what L is going to be simply 2, S, P and D. So this is L is S means L is equal to 0, P means L is equal to 1 and D means L is equal to 2. So L or orbital angular momentum of this electron L is equal to 2. Since its value of this S or spin angular momentum of this is going to be simply half, and therefore the quantum values I'll get here I'll get this is S is equal to 2, L is equal to 2, S is equal to half, and therefore it's J or total angular momentum is addition of this L plus S, and this addition gives me, again there is a vector addition we have to use, maximum to minimum or minimum to maximum. So L plus S and L minus S. So addition of 2 plus 1 half is 5 by 2, it is 2.5 or 5 by 2, and subtraction of 2 and 1 half is 1.5, that can be written as 3 by 2. So 3 by 2 and 5 by 2, these are the two possible values of G. In between quantum value is not allowed or not needed there. 5 by 2 is 2.5, 3 by 2 is 1.5. In between that fraction is never allowed. So 2J values are possible. So that shows L is equal to 2, S is equal to 1 half, and J is equal to 2 values 5 by 2 and 3 by 2. Therefore, amongst given options, A is L2 is equal to 1. That is not correct since it's a d electron. L is equal to 2. Option B. S2 is equal to 1 half. Since this is electron in the d state, we have written in spite of here I have written L and S, we can write to be L2 and S2 2. So L2 is equal to 2, S2 is equal to 1 half, and J2 is equal to minimum 3 by 2 and maximum 5 by 2. Third option, L2 is equal to 1. This is also not correct. Third option number D, that is L2 is equal to 3. This is also not correct because it is d electron. So L can take values only 2. So L2 is equal to 2, S2 is equal to 1 half, and J2 is equal to 3 by 2 and 5 by 2. So naturally correct option for this question number 8 is B as shown in this case. Now question number 9. For LS coupling schemes, the spin orbit interaction energies, which of the following statement is true? There are actually, when we have this two valence electron system, we have S1 and L1. These are the orbital angular spin angular momentum and orbital angular momentum of first electron. Similarly, S2 and L2. These are the orbital spin and orbital angular momentum of the second electron. Now here the spin orbit interaction gives you, first interaction is S1 and S2, that is given by this gamma 1. Then second interaction is given, not F, this is gamma. Then second is L1 and L2, this is your gamma 2. Then L1 and S1, this is gamma 3. Then L2 and S2, this is gamma 4, and remaining that is L1 S1. Okay, L1 S1, L2 S2 we have taken. Remaining this are this gamma 5 and gamma 6. So in all 6 such type of interaction energies, spin interaction energies are possible. So out of these two, gamma 1 and gamma 2 are dominant in this LS coupling over this gamma 3 and gamma 4, and as this gamma 5 and gamma 6 are very small or negligible, they are directly discarded. So this is the theory, or this is the concept where LS coupling has been applied for spin orbit interaction for two valence electron system. Therefore, amongst the given system options, option A is gamma 1 and gamma 2 are predominant over gamma 3 and gamma 4. This is the correct option. Gamma 5 and gamma 6 are negligible. This is also correct option. Gamma 3 and gamma 4 are predominant over gamma 1 and gamma 2. Now depending upon the LS or JJ coupling, if I am using JJ coupling, then this statement would have been true. As I am using LS coupling, first A statement is true. This gamma 1 and gamma 2 are predominant over gamma 3 and gamma 4. And therefore option D's statement A and B both are true, and this is what my correct option of this question, neither this or this. So question number 9, for LS coupling schemes, the spin orbit interaction energies, which of the following statement is true? So gamma 1 and gamma 2 are predominant over gamma 3 and gamma 4. Gamma 5 and gamma 6 are negligible. This is the actual LS coupling scheme. So both statement A and statement B are true. So in theory, you might have gone across all these gamma 1, gamma 2, gamma 3, gamma 4. These are interaction energies, and expression for that which are given as in the next example as question number 10. So come to the question number 10. This is again given you a PD configuration. So PD configuration of interaction energy gamma 1. As I said earlier, gamma 1 is the interaction energy between S1 star and S2 star. The spin orbit spin angular momentum of first electron and spin orbit momentum of the second electron. Resultant of this is given by S star. S star is given by S1 star plus S2 star and their addition and subtraction and so on. And therefore, using this theory, we come across several types of relations for this gamma 1, gamma 2, gamma 3, gamma 4, etc. So in one of the relation we come across, or you might have drawn this type of diagram. We write this to be a draw. This is S1 star, this is S2 star, and this is the resultant capital S star. So we show this is the precession of this S2 star. We show this is the precession of this S1 star, and this is what the precession of this S star around this. So this type of vector diagram which already we draw, this diagram shows you this S1 star and S2 star precesses around their direction of this resultant S star, and therefore we come across this type of terms here which we are shown here. This gamma 1 is equal to 1/2 into A1. A1 is the constant there. In the bracket it is S star square minus S1 star square plus minus S2 star square. Then gamma 1 B option is gamma 1 is equal to 1/2 times A1 into S star square plus S1 star square plus S2 star square, and gamma 1 C option is 1/2 times A1 into S star square minus S1 star square plus S2 star square. And here in the fourth option we just change the symbol here, plus minus minus to plus and plus to minus. So out of this combination is most correct, because this vector atom diagram that tells you this gamma 1 terms or the interaction energy between the spin interaction of this PD in electronic configuration, configuration of an electron to valence electron system. This is given by this expression 1/2 times A1 into S star square minus S1 star square minus S2 star square. So my suggestion is that go for actual theory of this. That theory tells you why this type of resultant we get. So the interaction energy for the spin interaction of PD configuration electron is given by option A, which is given by this expression. All the expressions look similar, but one of the signs of this plus minus we have changed, but accordingly when we go for these changes of the signs, the resultant actually is found to be something different, and that's what these are the not correct options. So correct option of this question number is A, that is given as there. Okay, then question number 11, as we have already discussed, in case of the two valence electron system, it is generally observed that dash dash levels lie above the corresponding dash dash levels. So there are singlets and triplets, and which one lies above and which one lies below, that is to be discussed from this particular example. Okay, thus in general when we go for any of the configuration like PD configuration, you might have used this PD configuration. In this PD configuration, if this is the average of this PD energy level, then these singlets are usually observed. This gamma 1 gives you this separation between the singlets. If this is the average of the singlets, then this separation between the singlets, which is given by this gamma 2, second interaction gives you this separation. So we can go for this calculation. Similarly, this gamma 1 gives you triplets, average of the triplets is given this. Then second separation gives you these averages of 3 triplets. Some triplets are above this average, some triplets are below this average. Further, this gamma 3 plus gamma 4 gives you this separation between the triplets, and this is how the scheme we use in case of calculation of all these singlets and triplet there. So in any of the configuration, it is usually observed all the singlets lie above all these triplets. Even the average of singlet is higher than the average of these triplets, and that's why in this case two valence electron system, it is generally observed that the singlet level lie above the corresponding triplet level. So there are 4 options. Option A is singlet triplet, option B is triplet singlets, option C is doublet. This is not at all applicable. So C and D are not applicable, and according to this theory, the correct option of this question number is 11 is A, that is the singlets and triplets. So usually singlet levels, energy levels lie above these triplet energy levels, in the PD configuration or any of the configuration when we go for this interaction energies gamma 1, gamma 2, gamma 3, gamma 4 and so on. Then question 12. According to the Hertz rule, all terms with the same value rule applied for LS coupling states that out of all terms with same L values arising from any given electronic configuration, a term with highest dash dash will lie deepest. Now there are four options given. Option A is energy, option B is angular momentum, option C is multiplicity, and option D is the interaction energy. So this is what a straightforward rules. That rules tells you multiplicity plays a very vital and important role. Therefore, the term with highest multiplicity lie deepest. Therefore, correct option of this question number 12 is C, that is multiplicity. A term with highest multiplicity will lie deepest, and the term with the lowest multiplicity that lie the top of this particular energy level diagram when we draw. So this is straightforward and a description of this Hertz rule. Question number 13. According to the Lande interval rule, for a given triplet, each fine structure term difference is proportional to the dash dash of two J values associated with this. For example, I have J values equal to 1, 2 and 3. Okay, so now difference here, these are the two values, largest values 2 and 3, and when we go for actual separation of any of the triplet, this separation is shown to be proportional to this is 2 and this is going to be 3. So this is what the rule tells you. So this separation is 3 and this separation is related to 2. So this separation, that is what this question, according to Lande's interval rule, for a given triplet, each fine structure, this is fine structure difference, is proportional to larger of the two J values associated with it. Now there are three J values. This is not proportional to these two J values, but this is proportional to these larger J values, and therefore question number 13, it is B. Answer is B, larger two J values associated with it. So no smaller, neither larger nor smaller, and none of this, no option is correct other than this option B. So it is proportional to larger J values. Then question number 14. In case of two valence electron spectra, of the following which statement is true? Now this is a very general statement. The spectrum mainly consists of singlets and triplets. The spectrum mainly consists of doublets. The spectrum mainly consists of doublets and triplets, and the spectrum mainly consists of singlets and doublets. So don't worry, you will find that in all such type of two valence electron systems, doublets are not absorbed at all, not observed at all. Therefore this option B, option C and option D all are incorrect, and therefore correct option is only A, that the spectrum mainly consists of singlets and triplets. Few singlets and more triplets are observed because of the spin orbit interaction of two valence electron system. That's what we will get the difference when we go for actual comparison of the spectrum of sodium and spectrum of helium or any other alkaline earth element. You will find out more and more triplets and singlets will be observed in this two valence electron system. So this is a theoretical question, we need not worry about this. Question number 5. In a helium atom ground state, both the electrons are found in. Now we have to go for this electronic configuration. Electronic configuration for helium is simply 1s2, and this is nothing but your K cell, and therefore option A is correct. Now this L cell, M cell, etc., there are no electrons available, these are empty cell, but one of the electron either can go in K cell or can go in M cell, and corresponding transitions whenever possible, interactions of this 1s electron and the electron in L cell or M cell, different types of combinations are possible, and accordingly spectrum of this helium becomes more and more complicated. So this about that, some examples we are going to discuss as follows. Now question number 16. The electronic configuration for helium atom is, as it is content of two electrons, so in the ground state the electron configuration is simply this is 1s1 or and 2s1, 2s2, then this is excited state, 1s0, 2s0, this is also not possible, and 1s2, this is the electronic configuration or correct electronic configuration for this helium atom. So in helium atom, this is nucleus which contains two protons and two neutrons, and the 2 electrons that are revolving around in the first orbit, that is, it is given by 1s2. And these electrons, they can go in 2s, they can go in 3s, they can go in 2p, etc., all other higher excited states, and thereby transitions are possible according to certain selection rules, and that gives rise to some singlets and some triplets, and that's what its spectrum is more complicated as compared to the spectrum of hydrogen as well as the spectrum of the sodium. So 2 valence electron system, the best example of spectrum is the helium spectrum. Now question number 17, helium spectrum, the singlet system belongs to. Okay, now there are 4 options. Option A is parahelium, spin are antiparallel and s is equal to 0. Orthohelium, spins are parallel and s is equal to 1, capital S is 1. Both para and orthohelium, and option D is neither of these. So naturally, when we go for singlet system, we have multiplicity is equal to 1, and this multiplicity is given by twice s plus 1 is equal to 1, and therefore from this calculation one gets twice s is equal to 0 or s is equal to 0. Therefore the case when this total angular momentum of the system of 2 valence electron system is s is equal to 0, the spins are anti-parallel to each other. So this is spin up and this is spin down, both one up and one up. So total spin in this case is equal to 0. When it is 0, multiplicity is 1, and such states are called as singlets. So basically, when we go for this type of helium, which gives rise to anti-parallel spins, or s is equal to 0, multiplicity is 1, then singlets are possible, and therefore it is called as a parahelium. So in helium spectrum, singlet system belongs to the parahelium, and naturally when s is equal to 1, then this multiplicity twice s plus 1 is equal to 3, and that gives rise to triplets. So the spectrum, say in the helium spectrum, when we have spins antiparallel of both of these electrons or parallel to each other, then such system gives rise to a orthohelium. So spectral lines of this orthohelium mainly consist of triplets, whereas spectral lines of helium mainly consist of singlet. Spectral lines of when there are say singlet spectral lines, that is called as the perihelium. So in general, when we get a gaseous or total spectrum of the helium, it is found to be a mixture of orthohelium as well as perihelium. That is what we are going to have some question next to that. Then question 18, in helium spectrum, the singlet terms arise when one electron remains in 1s level and the second is excited to a higher energy level with spin. Okay, so again, singlet means the spins of one of the spin is up and one of spin electron spin is down, and therefore capital S is equal to 0, and again it is twice s plus 1 multiplicity, that gives you equal to 1, and singlet states are possible. That means one electron should be there in one state, and second electron either goes into 2s or 2p or whatever, and the spin of that electron is found to be antiparallel. So when they are antiparallel to each other, then s is equal to 0, then m is equal to 1, and then it's singlet. Therefore option B is the correct option of this question number 18. So in the helium spectrum, the singlet terms arise when one electron remains in 1s level and the second is excited to higher energy levels with spin anti-parallel to the first electron. So when the spins remain parallel, then it gives rise to triplet in the spectrum. When spins are the anti-parallel, this is excited, then this is gives rise to a singlet. So this is to be understood from this helium spectrum when we go for this study of the orthohelium and parahelium and so on. Then this is the same question. In helium spectrum, the triplet terms arise when one electron remains in 1s level and the second is excited to higher energy level with spin dash to the first electron. So again, parallel, anti-parallel, perpendicular, and any random direction. Out of this, option A is the most correct option, because both the spins, excited and non-excited electrons, these are parallel to each other. So S is equal to 1 and twice S plus 1 is equal to 3. That is what this gives rise to a triplet system, and that's how we will get these spins are, both of these electrons are to be parallel. So question number 19, correct answer is E. Now ordinary liquid gas or gaseous helium is Option A, perihelium. Option B, orthohelium. Option C is mixture of para and orthohelium, and option D is neither of this. So according to this theory, what we have seen, it is always a mixture of para and orthohelium. Therefore, correct option of this question number 20 is C, mixture of para and orthohelium. Now the lowest state of orthohelium is, okay, see the lowest state of orthohelium. Ortho means one electron is in the up state, first one in this 1s1, and second electron is either 2s1 or whatever, it is also in up state, and therefore if we go for the lowest state of this particular system, that can be seen as, or that can be obtained as. So in orthohelium, one of the electron goes into the state that is called as 2s1. So here in this, these are one is this principal quantum number, here is 1, principal quantum number for this electron is 2. So I can write this 2 is the n value for this. Now for the second electron and first electron, values of s1 and s2 are simply s1 plus s2, that is 1/2 and 1/2. Since both the spins are parallel, capital S is going to be 1. Therefore multiplicity here also twice s plus 1 is going to be 3. That's what I am supposed to get multiplicity. So, and one more thing is that since it is in S state, that is how we are going to get the S state. Then it is a triplet, and similarly this J value in this case, if I go for this calculation of J value in this case, since this, sorry, we have made a mistake here. This, since this is in 1s and this is also 1s, both the values of L1 and L2 are simply 0 and 0. S1 and S2 are 1/2 and 1/2. So in this case, calculation of this L1 plus S1 gives you 1/2, as well as calculation of L2 plus S2, that also gives you 1/2, and therefore this J value is simply given by L bar. Since 0 1 L bar, L1 and L1 bar and L1 bar to 0 0. Therefore this, I guess, J is equal to L bar plus S bar, and that is also simply actually in this case, so L1 and L2 are 0 0. So this I'll get this this is J1 in this case is 1/2, and J2 in this case is also equal to 1/2. So both addition of this is J1 and J2 is 1/2 and 1/2, and therefore capital J is equal to addition of J1 plus J2 and subtraction of J1 minus J2. So addition gives me value to be equal to, that means addition gives me this is to be simply equal to 1. 1/2 plus 1/2 is 1, and this is the called as the ground state or the lowest state, and that's why 2. Then it is, since S state, it's a triplet state, and there is the value of J is equal to 1, and that's why 2 triplet S1, this is said to be the lowest state of the orthohelium. So we can calculate this using this two valence electron system, writing their values of L1, L2, S1, S2, and applying the schemes. We can go for this type of calculation. Therefore lowest state of orthohelium is 2 triplet S1, that is shown as by this particular simple example. Then question number 22, I think this is probably last question. The fine structure of very narrow orthohelium series triplet was verified by, actually it was predicted by Slater, and it was verified by the Heisenberg, and therefore correct answer of this question number 22 is this Heisenberg. So if we go for consideration of this entire chapter, you'll find this two valence electron system, the schemes which we apply, that is LS coupling type of scheme, JJ coupling type of scheme, how to obtain the term values for different types of combinations like PD electron, like SP electron, and so many, and the singlet triplet separations, the Horn's rule, the etc. These are the important things that we have to go for consideration when we go for solving different problems here. But as compared to chapter 1, this chapter 2 has some more conceptual problems, and that's how it is bit not difficult, but it is much mathematical as compared to chapter 2 and chapter 1 as well. That's why these are the important questions we have discussed here. I hope again this video will found you, it will be useful for you for preparing this forthcoming examination. In the next session we are going to see the remaining chapters of this atomic and molecular physics, or remaining chapters of that will be discussed again for 20-25 questions for each of this. So till then,